Hello and welcome to this module on artificial neural networks. So artificial neural networks were a computing model inspired by biology. So we have neural network architectures that have been proposed for a variety of different analytics tasks like regression, classification, clustering, feature extraction, etc. So these architectures essentially are networks of simple computing entities. Right? So this is like a very simple threshold entities that are connected together in a specific network architecture that give rise to complex computing functionality. Now, of late, there has been a significant resurgence in interest in artificial neural networks, especially under the domain of deep networks, about which we will see in one of the later modules. Right? So, as far as this module and the discussion about artificial neural networks is concerned, in this course, we will look at only the classification task, and many of the ideas we talk about here for classification are generalizable to regression. Right? While for the other kinds of analytics tasks, we will need different architectures, but we are not going to cover that in this course. So the inspiration comes from biological neuron. So let's not worry about the complete complex structure of a neuron. What we really have to focus here is on the input and the output. So the neuron receives inputs from the dendrites or from the dendrite branches from other neurons, and when the input signals is above a certain threshold, it's going to produce an output that is going to be transmitted via the synapses to neurons that are further down the line. So these connections through the dendrites and synapses are going to result in a very complex network, and even though the computing done by each element is a very simple summation and thresholding, the sum total of this taken across the entire network can give rise to really complex computations, as we will see. Right? So the computing unit is something that's very simple. So it's going to take a set of inputs x1 to xn, and it's going to compute some function on it. Okay? The function is very simply computable, and then it will produce an output. Right? So we'll look at what this function is going to be in detail in the next few slides. Right? So the initial model for this for a biological neuron was proposed by McCulloch-Pitts in 1943. It's called the McCulloch-Pitts Unit. Okay? It used only binary signals, so zeros and ones. So either an input is active, in which case is represented by 1, or if it's not active, in which case is represented by 0. And the nodes also produce only binary results, so the outputs could be either zeros or 1. So the edges between these different nodes were directed, unweighted. They could be of two types. They could be excitatory or inhibitory, and again, like I mentioned earlier, they transmit binary signals. So what is the computation that happens here? So let's assume that the McCulloch-Pitts unit gets input x1 to xn through n excitatory edges, so these are positive edges, and inputs y1 to ym through m inhibitory edges. So that means these are edges that could produce a depression in the function or could actually stop the functioning of the neuron. So the assumption that was made is if m is greater than or equal to 1, that if there is at least one inhibitory edge, right, and if any one of the inhibitory edges is 1, right, so if there is a one inhibitory input, then the unit as a whole does not produce any output, regardless of what the inputs x1 to xn are. Right? If none of the inhibitory inputs are 1, or if there are no inhibitory inputs at all, okay, the unit computes the summation of x1 to xn, right? Let's call it x, and if x is greater than a threshold that is specified for each unit, so if it's greater than a threshold theta, then the result of the computation is a 1, else the result is a 0. So that's very simple. So essentially you can think of it as adding up all the inputs that come to the neuron, right? And if the summation is greater than a threshold theta, the output 1, otherwise the output 0. So the inhibitory edges in some sense here act as a gating signal. So if it is 1, the output is always 0. If the inhibitory signal is 0, then the output is the result of the computation. Okay. So this essentially the McCulloch-Pitts unit is implementing this threshold function. If the input is below theta, you are going to see an output of 0. If the input is above theta, you are going to see output of 1. So this is essentially a step function. So what kind of computations can you do with this? So you can actually do almost all your familiar Boolean operations with a McCulloch-Pitts neuron. Right? So you can think of doing an AND operation. Right? where you have two inputs x1 and x2 and the threshold is set at 2. Right? So if only both x1 and x2 are 1, so it will be greater than or equal to the threshold and therefore the output will be 1. And for implementing an OR, you can set the threshold at 1. So if either x1 or x2 is 1, then the output will be 1. How about implementing a NOT unit? We can implement a NOT unit by having x1 act as an inhibitory input. So this circle here indicates an inhibitory input. So if x1 is 1, that means this the neuron will be inhibited and the output will be 0. On the other hand, if x1 is 0, then the output will be whatever is according to the result of the computation. But you can see here that the threshold for this neuron is set at 0, and therefore the output will always be 1 as long as there is no inhibitory input. Right? So if x1 is 1, then the output will be 0. If x1 is 0, output will be 1. Therefore you have implemented NOT function. So once you are able to implement this kinds of AND, OR and NOT, then you know that you can connect all these neurons together and then implement any Boolean function that you want. Right? But is this what really we are interested in? Right? So we are not really interested in that because we want to be able to do more complex classification problems where we would like to learn simple things like linear surfaces or more complex surfaces that separate two classes. Right? So that has been the goal of classification we have looked at so far. So in 1957, Rosenblatt proposed a very simple extension to the McCulloch-Pitts model, which he called a perceptron. The more crucial thing about the perceptron is that it introduced weights at the inputs. The crucial differences from the perceptron from the McCulloch-Pitts model is that the perceptron introduced weights at the input, right? And then the output could be either a 1 or a -1 depending on whether the weighted sum of the inputs is greater than a threshold or not. Right? So it's a computing unit with a threshold theta. So I'm just repeating it. So the output of the neuron is 1 if the weighted sum of the inputs is greater than or equal to theta. It's equal to -1 otherwise. So what is the goal here in perceptron learning? In perceptron learning, we are essentially trying to learn a hyperplane, right? Or trying to learn a separating surface as we have done in the past in the other classification problems. We are trying to learn a separating surface that can separate one class from the other. So what would the classes be in our case? Classes in our case would be +1 and -1. So this essentially means if wi xi is greater than or equal to theta, it essentially defines the equation of a hyperplane as we have seen in the previous modules, right? So if we can take the theta to the other side, so it could be like wi xi minus theta is greater than or equal to 0. So we have seen that. So if it's greater than 0, it is on one side of the hyperplane. If it's lesser than 0, it is on the other side of the hyperplane, and we are going to say that data points to one side of the hyperplane belong to class 1, data points to the other side of the hyperplane belong to class -1. Right? So now the question is, given a set of training data, right, that gives you the the vector x and the desired output y, how would you find these weights wi's such that the perceptron is actually implementing that hyperplane, right? Implementing the right separating hyperplane. So the way to do this is follows. You start off by randomly initializing the weights to some value, and then you look at the prediction that is made by the weight, right? So the prediction that is made by the current setting of the weights, let us call it O, right? And the target is the true class of the data point x. Right? So that's so it could be either +1 or -1, and likewise O is also +1 or -1. So your goal is to make sure that your perceptron output matches the target value. So the perceptron training algorithm has a very simple rule. So at every presentation of an input point, you change the weights by an amount that is proportional to the difference between the target value and the actual output produced times the input on the particular bit. So wi changes by an amount that is proportional to t minus o times xi. So eta here is a small constant, maybe 0.1 or 0.01. It's called the learning rate. So one thing to note here, if for a particular input x I produce the correct output. If the class is -1 and I produce -1, if the class is +1 and I produce +1, this expression, right, evaluates to 0. Right? You can see that this expression evaluates to 0, and therefore no changes in the weights will happen. So essentially what happens here is you change the weights only whenever you make a mistake, and that too you change the weight proportional to the input variable. So if xi is say a small value, say 0.1 or 0.2, then the changes in the weight will be small. And as opposed to when xi is a large value, let us say 1 or 0.95 and things like that, then the change in the weights will be large. So this is essentially because the larger the input variable, the more important it is going to be in the prediction of the output, at least in the way we have set up this perceptron. Right? So that's essentially the simple training rule. So whenever you make a mistake, right, you take the vector for which you have made a mistake, right, add some small fraction of that vector to the weights. Right? So this looks like a very simple rule, but then back in the 50s, right, this perceptrons created a lot of hue and cry. People saw that the perceptrons were able to learn from scratch, okay, trying to solve some things which were considered hard learning problems, and then they used the perceptrons, they were able to solve that. Right? So much so, you can see here the hype was that they are going to build a computer that expects to be able to walk, talk, see, write, reproduce itself and be conscious of its existence. Such a significant amount of hype, and it's always hard to live up to any hype that is so disproportionate to the actual effect that was achieved at that point. Right? So let's take a look. Let's just step back and take a look at what can a perceptron learn. I mean, is that newspaper article really true, or what are the limits to the perceptron's learning ability? Okay. So here is a very simple perceptron here. Okay, so it has two input variables, x1 and x2, and has a threshold of 1, right? And the weight w1 is 0.9 and w2 is 2. So if you look at it, essentially it implements this straight line here. So everything above the straight line, these light colored regions belong to one class, and the dark colored regions belong to another class. So we know that these are data which are linearly separable. Right? We saw this in the case with SVMs. So these are data that are separated by a linear hyperplane or a linear separating surface. Right? So all the data points for which the W transpose X evaluates to greater than 1 will get a class of +1. All those that evaluate to lesser than 1 will get a class of -1. Right? So again, let's go back and look at the simple logic function that we saw earlier. So it can implement an OR. Right? So essentially OR requires you to have a hyperplane that is passing here. So everything to this side is become +1, everything to this side becomes -1. And likewise you can implement AND. So you can draw a simple hyperplane. So everything to this side becomes +1, everything to this side becomes -1 or 0, I mean, depending on how we want to interpret the output. Let's look at another one. Let's look at a simple problem, just like OR and AND, the XOR problem. Right? So Minsky and Papert in 1969 in a famous monograph called the Perceptrons showed that, well, a simple problem like XOR, right? So where the truth table is given here, if the inputs are the same, your output is 0. If the inputs are different, your output is 1. Right? A simple problem like XOR is not linearly separable. You cannot draw a hyperplane that separates these two classes. Right? So forget about walking, forget about talking and doing all those wonderful things that were claimed in the newspaper article. Perceptrons cannot even solve such a simple problem as XOR, which essentially says that two things are same, your output is 0, two things are different, your output is 1. And if it can't recognize the similarity between the simple inputs like zeros and ones, where can it do complex computations? Right? So once Minsky and Papert showed this, it's kind of dampened the research into neural networks for a long time until there was a revival much later. Right? So perceptrons can learn only linear decision boundaries. That's the takeaway message here. Okay? So does this make this whole idea of neural networks completely useless? Because if they can learn only linear decision boundaries, in case of SVMs, we saw that we could get it to do non-linear boundaries by going into a kernel expansion. Is there something similar that we can do here? Let's look at let's look at how we can change the representations, right, and try to do something more clever, right. So if you look at the original problem, the XOR problem, so I have my inputs x1 and I have my input x2, and now we can see that in this space the problem is not separable, right? But let us do a simple transformation on my data points. So instead of looking at x1, I'll define my first variable as not x1 and x2, right? And similarly I'll define my second variable as x1 and not x2. So if you think about it, so you can now plug in different values of x1 and x2 here and see what the outputs will be, and then you can see that when x1 is 0 and x2 is 0, the output is going to be 0, right? When x1 is 1 and x2 is 0, right, see the output here will be x1 is 1 and x2 is 0, the output here will again be 0, and x1 is 1 and x2 is 0, the output here will be 1. And we know that 0 1 the output has to be 1, so that we get it here. And likewise for the symmetric case, this will be the output, right? And so you can see that this is again going to be 1, and when x1 x2 both are 1, again the output will be 0 0, and therefore this is the resulting point. Now obviously with this representation, right, the data points are linearly separable. So now the task becomes one of finding the right representation such that the data becomes linearly separable for the next level, next stage of computation. Right? So people realize this very quickly. So even though a single perceptron cannot solve complex problems like XOR, right, which are not linearly separable, you could actually stack layers of neurons and then have the first layer compute something that is simple, right? So you can always compute not of x1, we saw that earlier, and also can be computed by a single neuron, right? So you can just have layers of neurons that essentially compute your features and of not x1 comma x2, and then have another neuron, right, which takes the output of these neurons, combines them together and produces the output that you want. So people very quickly realize that stacking these kinds of neurons into layers, right, allows you to do more complex computation. In fact, it is easy to show that stacking these neurons into layers actually builds a universal function representation that allows to represent any Boolean function using a combination of neurons. Okay. So what is the problem? Now we know how to solve this more complex problems. Why didn't the research in neural networks pick up again? Right. So the question here is, when I start connecting all of these neurons into layers, right, how do I find the weights? Right. So the perceptron learning algorithm might no longer work in this case, right? Actually does not work in this case, and people were struggling to come up with a mechanism for training all these weights. Right. So you can see that now we have started putting these things into layers. So there is one input layer and one output layer. So there is one input layer, there is one output layer, and in between this you could have many layers of neurons. They are typically called hidden layers because you don't observe their outputs directly. Right. Right. So now we have this many hidden layers of weights, and we know it's little hard, right, to find out what these weights should be. Right. And so in the mid 80s, around 83, an algorithm was proposed called backpropagation, which allowed you to learn the weights of all these hidden layers, right? So for the rest of the presentations, we'll be looking at the standard 3-layer network, right? So there is an input layer x1 to xd, okay, and the output layer, okay, which we will denote by f of x, right? And one hidden layer of neurons. So these take the inputs from the input layer, do the weighted sum, do your thresholding function, and then will produce an output. And then the neuron in the output layer will take all these outputs of the hidden neurons, take their weighted sum, and take the threshold or not, and then produce the output. Right? Instead of using instead of using a hard threshold, you use a kind of a soft threshold. Right, in order to do these computations. This is needed so that we can derive more efficient training algorithms later. Right? So the output of the hidden units will be given by g of the bias term. This is the theta that we had earlier. So instead of theta, so we're going to call it b1 and plus w1 times x. Okay, and the output of this will be denoted by h of x. And the output of the final layer of neurons is given by some function O of b2 plus w2 times h of x. Right? And so now the goal here is to figure out what this w1 and w2 are going to be. So this is called a 3-layer network, even though there are only 2 sets of weights that we have to learn. So the layers here talk about the neurons here. So we use for each input variable, we assume that there's a separate neuron that is activating the hidden units. Right? So this is called the standard 3-layer network structure. Right? So what are the different activation functions we can use? So we already looked at one, which is the threshold function. Right? We can also have just a linear activation function that basically takes the weighted summation of all the inputs and outputs it as it is. Right? We can also look at the sigmoidal function, right? Sigmoid logistic function, which takes the summation input and then squashes the input so that it lays between 0 and 1, right? And then there is a steep rise somewhere around the threshold, right? So that it transitions rapidly from 0 to 1, right? But if you're interested in having signed outputs, then you can think of using a hyperbolic tangent, where the outputs are going to transition between -1 and +1 and again around the threshold. So there are parameters that control where the threshold would be and how steep the rise would be. Right? So another transition function is sometimes used as a squashing function, which is 0 before the threshold and 1 at a certain distance higher than the threshold, and in between you have a linear approximation to the step function. Okay, this is called the squashing function. Right? So typically in most of the neural network architectures that we will look at, we will be looking at either the hyperbolic tangent or the logistic sigmoid or the linear activation, right? Because these are differentiable and this allows us to derive efficient training algorithms for the same. If you are doing a classification problem, then the output layer could be either a hyperbolic or a logistic sigmoid, and if you are solving a regression problem, the output neuron could be a linear neuron, so that you can do appropriate regression fit. Right? The hidden layer almost always has to be a nonlinear function, and with a little bit of work you can show that if the hidden units have a linear activation, right, you might as well not have them at all. And what is the function that is implemented is something which can be as well implemented by a single layer of neurons. Right? And so we will look at the next module. We will look at how you would exactly find out these weights, given the assumption that you are working with a sigmoidal logistic function. So the function for the sigmoidal logistic thing is given by f of net is 1 by 1 minus e to the power of minus net. So that's the function, and we look at, given that this is the activation function, how we are going to derive the weights of the 2-layer standard 3-layer neural network. So that's in the next class.